Yeah, hi everyone. So today is the opening session for week 10.
Hello, good evening, sir.
Good evening, Harshit. Okay, so how's your preparation is going on for the quiz 2?
Sir, I am actually in week 6 right now. Week 7, I started for revision.
Okay, so week 7 will be start. Good. Okay, so tomorrow is the revision session for week 5 and 6. So you can ask your doubt.
Okay, okay.
And then the day after tomorrow for week 7 and 8. Okay. Okay, so for others, if you have any query, uh, I think you have seen the video of week 10. Have you all started to watch the video of week 10 or not?
No, sir.
Okay. 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 So I am revising all the topics of week 10, starting from the first topic. Just yeah, AP, you can ask. What's your doubt in week 3? AP, you can unmute yourself and you can ask.
Yeah, good evening, sir. So I was kind of doing the week 3 lectures again. So I had a doubt in, I think it was lecture 3.6, I believe, designing a flexible list and operations of the same. So it was, my doubt was on the insert operation on the flexible list, right? So in the linked list, I mean, the way sir explained it, I couldn't understand it quite easily. So if you would be, if you'd be able to explain it again, it would be really helpful.
Okay, so actually, sir, explain this insertion operation using the recursion method. So actually, sir, create a linked list using the recursion methods. So if you see the code, both codes are available here. Week 3. This linked list. Yeah, this one. So yeah, this is the code which sir used in the lectures. So sir used only one class to create a list, and here the first node actually contains the first node value, as well as this node is also representing a head position. Okay, here actually we are using as a first node as two identification, so that also contains a value of the first node, and also that is also identify the starting of the node in the linked list. So there are so which operation you are facing issue? Actually, there are two types of insertion.
Insert operation. So the
Insert
one where we, insert a value at the front of the list.
front of the list, no? Yeah, okay. So insert 7.
So
Okay.
in this, I was like, sir said that we are not able to directly insert something.
We cannot insert directly, and we will insert at the second position, then we will swap the value, this type of thing.
Yes, and then we swap the values, right? So that's what my doubt was. I mean, why can't we do it?
Okay. So actually, sir is creating a linked list like in this format. So for example, this is a first node, and there are two parts like in this format. Okay, and this node is creating using a only one class. Okay, so if you see the class, so the class name is node. So initially when we create the first node, so we just write that a equal to node like this. Okay, so at this time, when we are creating a first node of the class, that means this a object is representing a head position, head position of the linked list. Okay, so when we are creating a object for the node class first time, so that is also, so that a object is also representing a first position, head position of the linked list. That means the first node. So if you want to insert, insert any value at the first position, so so you how you can change that. So after so for example, after creating a first node, at the second time when we are inserting a node after that, so we are recursively call this class inside. So for example, we have started so that is showing the code. If you see the append code, okay, if you see the append code, so here we are just checking, we are just inserting in the self, and we are just accessing these first node as a self. After that we are calling this class recursively. So since you can see that we are just calling the node recursively inside the same class. So when we have created the first node, after the appending the second, third, fourth node, we are just calling the same node class recursively inside it, and we are adding the nodes. So that means first node reference is contained by this object a. So when you want to insert the new node at the first position, so you have to change the reference of this node. How you can change this reference? Because this a is the first creator when we create the first object of the class. This is referencing a first node. So how you can add the new node at the uh, how you can insert new node before this node? So you have to change the reference of this a also. So we if you change the reference of this a, you will lose the reference of this whole list.
So can't we just, kind of alias a and then change a afterwards? Can't we just, keep the value of a in a variable, say temp, right? And then we, create a new node and
So but
just.
we are performing this insert operation inside this a node, inside this class. At the same time, you are changing the reference of this a node. How you can do this? We are performing this operation when we have created the a node. After that, we are performing this insert operation, and you are
Okay.
performing all these operations using a self, and self is representing a reference of this object. And how you can insert the new node at before that? That means you have to set the reference a to this node and the new inserted node to this node.
Okay, so you're saying that because the first node is self, so we cannot insert a node before that.
Yes. So yeah, since this is a age object of the first node, and this is also representing a head position of the list. Okay, if we remove this a, that means we will lose the complete reference of the list. If you are changing this reference of a here, you will lose the complete reference of the previous list, because this a contains the reference of the first node. And after creating this node, we are performing the insert operation inside it. We are performing insert operation using a self, and at the time of self, this self is representing a this a. So using self, how you can change the reference of the same object?
Okay, sir.
So there is one another way of implementation. If you have seen in the notes, we can separate the class where you can perform this operation which you want. Here you can see this implementation. We can create a separate class node. This is for node, and there is one separate class for linked list. Okay, and this linked list contain the reference of the head node. Node is created by this class node. Here we can insert the node at the first position, because we will not lose the reference of the head, because we have saved the head reference in the linked list separately. In this way, you can insert the new node at the first position without any problem. But in the previous, actually, we are performing insert operation recursively in the same class, inside the same class. So we cannot change the reference of the same class in which we are working.
Okay. Okay. So but logically, these two implementations using one class and using two classes, logically these things are the same, right?
Yes, both are the same.
Okay.
You can use any. Basically, we have to perform the concept of linked list. So you can use any type of the implementation.
Okay. So just one more thing. So one more doubt. I had one more doubt. So in lecture 3.8, so implementation of dictionaries. So the hash things. Can you please explain to me briefly again?
Okay. So in the same notes, you can see this diagram. Okay, what is hashing actually? Hashing is basically we generate the index, or we can say that we generate the address using a hash function, and this hash function takes the input key as so it takes the key as input. So for example, if we want to insert 10 in our, so this is a key, okay, and this is our table, okay, for a store, and this table containing 9 index. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 index. Okay, and we have a one hash function formula. For example, this k mod 10. Okay, this is a hash function. Okay, so there are many hash functions are available in practically, but we are using this simple hash function here. Okay, now we want to store one value. For example, we want to store 14 in our this table. So we will calculate the index using this hash function. So we will just give this 14 as a key. So 14 mod 10. So it will return the 4, and that means we are generating an index using a key. Okay, and at this key we directly store this value 14 here. So this is a one operation. We can say this is a constant operation. Okay, we are just we are creating we are identifying an index using the key and using the hash function directly, and we are storing our key at the generated index directly. So this is the storing process. Same time when we want to search this 14. So for example, we want to search this 14. So we will apply the same hash function on that. So same hash function we will apply at the time of searching 14 mod 10. So it will return as 4, and then we will directly check the 4th index. There is no need to traverse the element one by one from the starting index for comparing where is the 14. So we will directly check the index which is calculated by the hash function, and we can directly access the value from the index which is generated by the hash function. So this is also a constant operation. That means we can store the element in a constant time, and we can also search the element in a constant time in our memory. So that is called the hashing techniques. Okay, so if you see that this
Okay,
diagram,
so and what about the collisions?
collision is that, for example, we have a hash function, this k mod 10. So k mod 10, and same times we have stored the value 14 at the fourth index. Now we want to store the 24 value. Okay, we want to store the 24 value using the same hash function and in the same table. So we will apply the hash function on the same. So 24 mod 10, it will also return the fourth index. Okay, that means two key is generating a same index. That is called the collision. So that means a second key is also generating a fourth index, and this fourth index is already occupied by this 14 value. So this is called the collision.
Okay, so and so to resolve this, I mean, sir
Yes.
said that we used two, two methods to resolve this: closed hashing and open hashing, right? So open hashing was fairly easy to understand, but the closed hashing thing, sir said that you just go round and round until you find a free space. So, but I mean, all of this, I mean, the free spaces, if there are free spaces, that means it's allocated for another value, right? So how can you just go about putting any and every colliding value into some free space?
So there are some methods inside the closed hashing topic. So there is one linear probing approach, and there is one also a quadratic probing approach. So there are also some another approach are also available. So here we just use these two types of approach: linear probing and quadratic probing. Okay, in the linear probing, basically what we will do, we will just check that if we are finding the collision. So for example, for this 24, if we are finding the collision at this time, so at this time we will check the next position. So next positions, we are getting this fourth index. If this index is not available, not free, then we will just check the next index 4 plus 1. We will check this space. If it is available, we will store the 24 value here. If it is not available, then we will again increase by 1. 5 plus 1, 6. We will check the next. Same things we will repeat till we will get the empty slot. That means we are just checking after calculating the first index using the hash function. If it is not free, we will check the slots linearly, one by one. After that.
Okay, so and if we do find a free space, for example, after 14, when we're trying to insert 24 into this, and after 14 we find that there's a free space immediately at 7, at index 7, right? So what happens if I after inserting 24 into the 7th place?
No,
what
we
happens
will
if I
not,
try to insert 27, for example?
So for 27, we will insert at the 8th index.
So in that case, wouldn't since we are inserting wherever we find a free space, wouldn't the whole system crash down? I mean, you're inserting a value, you're inserting a value instead of in its own designated place, you're inserting it somewhere else, right? So things
Actually,
are
this
not
is
where they're
not
supposed to be.
So this is a approach actually. So there is so currently we are using a different types of the hash function that generate the unique address always. So RSA algorithms currently we are using in our systems. So that is very complex algorithms. So that mostly generates the unique address for each value. But this is a basic hash function we are using to try to only for learning purpose. That type of hash function is not using practically. So this is the first linear approach. When we are finding the collision, we will just check the next location if it is available or not. So second approach is quadratic approach. In this approach, we skip the box using this formula. If you see that, so actually at the time of when we are storing, we will follow the same approach. At the time of searching, we will follow the same approach. So some linear operation may be performed. So but where the crashing will why the crashing will perform? Why you are thinking that crashing will happen?
So no, because I mean everything
So at the
isn't
time of
really
searching
supposed to.
so at the time, for example, this list is completely filled. Okay, this table is completely filled. Okay. So for example, we have say 14. After 24, we will store 24 here. Now we store 34, then 34 come here. And after that, we are storing 26. 26 is not, so 6 index is not empty. We will store 26 here. Okay, same when we will search the 26 search, so same process we will apply at the time of searching. We will check the 6 index first, then if it is not available on the 6 index, we will check the linearly after that if it is available or not. So at the time of storing, at the time of searching, we are performing the same operation. If we are using the linear approach at the time of storing, so linear approach we will use at the time of searching also.
Okay, so you're saying that I mean we'll be able to retrace our steps back to the value we desire, right?
Sorry.
You're saying that while searching, we'll be able to retrace our steps.
Yes.
Okay, and so what happens if this whole 0 to 9 list is completely full?
That after that, that means if memory is not available, how you can store the data?
So does an expansion of memory take place, or so because or does it throw an error saying that
So for example,
overflow or something?
if you are using 4 GB RAM, and if your 4 GB RAM is full, so definitely your phone is written the message your store is full.
Right.
Okay?
Right.
So that RAM is also memory where we store the data. If memory is full, so then definitely we cannot store the data after that.
Okay. And so what is the practicality of using this closed hashing technique?
Close hashing. Okay, so this things close hashing and open hashing. So right now, actually, these are the basic approach. Right now, the different types of approach are using practically. So currently, I don't know which. So I heard about this RSA algorithms, which we are using. So exactly which approach they are using in the Python, so I don't know these things. Said the Python, but in the dictionary, same concept is using. We are generating an index using a hash function. So what hash function they are using? These things exactly I don't.
Okay, sir.
Okay, so both of the operation searching and storing we can perform in a constant time using a dictionary in the dictionary.
Oh, okay, sir.
Okay.
Can
Okay,
you
thank you, sir.
explain the open hashing also, please?
So open hashing, basically we use the chaining methods. So there is one method is given inside it. There are also another methods are also available. So open hashing means we will store the data for the same index using a linked list. So for example, if we are getting a 0 index from the hashing functions, so we will create a separate chain for this 0 index. So for example, 40 will generate the 0 index, 60 will generate the 0
Okay,
index.
okay.
70 will,
For
okay.
all the things with whichever we
Yes.
get the zero index, we create a link clicks in that. Okay, okay.
Yeah, so we are just linking this all the linked list. We are linking this as a 0 with the 0 index. So at the time we are getting 0, so we will search this linked list linearly one by one.
So isn't this a much better way of dealing with collisions as compared to the closed hashing technique?
No, actually, but it will increase the time.
Because we have to traverse the whole linked list while we're searching for
Yes, the
values.
linked list actually takes the more space.
Okay.
Okay, so every time we use the two fields, one for the value, one for the reference, so that takes the extra space.
And also searching is not possible like close hashing, right? Like random access is possible here because of linked list. We have to go through each thing. Right?
Yeah, one by one.
Right. So the thing about random access is not kind of fulfilled here, right?
Random access, yeah. So actually, our memory is very big in nowadays. Okay, so mostly the hash function generate a unique, most of the time hash function generate a unique index. So this type of collision not occurs in practically. Okay, we are taking the small example, small tables, because of that you are facing this, you are seeing this collision. Otherwise, practically this collision, most of the time collision not occurs. So our hashing function is are designing in that way, so they not create a duplicate address.
Oh, okay, sir. Thanks a
Okay.
lot, sir.
Okay. So some other questions are also there. One second. Let G be a complete undirected graph on 4 vertex having 6 edge with weight 23.5. Okay, so there is one question from her sheet. Okay, I'm taking this. So let what maximum possible with that we can that a minimum weight spanning tree of G can have. Okay, so here the question is given. We have 4 vertex. Okay, so I'm just creating A, B, C, and D, and this is a complete graph. So that means all edges are connected. So after that, the weights are also given. So we can take the weights 1, 2, 3, 4, 5, and 6. These 6 weight we can take on the 6 edge. So the maximum possible weight uh, possible weight that a minimum weight spanning tree of G can have is. Okay, so you know the Kruskal algorithm steps. So if we assign the, for example, these are the weights in the increasing order of their weights, 1, 2, 3, 4, 5, 6. Okay, so for example, we are taking a weights in the increasing order. So one we can take. So for example, one is assigning at this age. After that, when we are selecting the second weight, so 2 we are selecting. So for we can take on this 2. So after that, we can ignore this 3, because if we take this 3 on the diagonal cycle edge, so if you see this A, B, D, A, so this 3 is creating a cycle. Okay, so we cannot select this because this edge create a cycle for our in our spanning. So at this time, we will take the 4 weight. For example, 4 is at in the here, and 5 and 6. So at this time, we can select 1 and 2 directly, but 3 we can ignore, because maybe 3, if 3 weight edge is coming and it is creating a cycle, so we can skip that. After that, we will select the next weight. So this is a 4. Okay, so this is the maximum possibility to make a so this is the maximum possibility of the weight 1 plus 2 plus 4. This is 7. So we cannot get any minimum spanning tree which contain more than weight for this 7. Okay, so this is the answer for this question, 7. Okay, Harshit. Okay, can we also use the list to implementation hashing? No, if we will use the list, so that is the different type of data structure actually. So how we can achieve this complexity constant in the constant time? If you are using a list, definitely list complexity you will get. So insert operation, delete operation. So how much time the list takes? Definitely dictionary will also take. So we will be able to access week 11 content and GitHub book only after week 11 contents get released. So actually on GitHub books, so no contents are available for the week 11. Actually week 11 mostly are the theoretical basis concepts are given. So you can learn these topics using the slides. And there is no programming assignment for week 11 are they available. So request help in week for PPA2 and PPA3 not able to start off. Okay. So PPA2 and PPA3, I think these are the big programming problems. So I think PPA2 find all path. Okay. Oh, this is nice. Okay, this is also big. So Bimles, we can discuss this programming problem in I think live coding session in any. So after the quiz. Okay, so I think it will take much time. So I think for one problem maybe take one session. This maze problem is a big problem. So
Yeah, that will be helpful. Why? Because
yeah,
even though on pen and paper, it seems okay, but difficult to put it.
okay,
in
yes,
code.
definitely we will discuss in any one of session after the quiz. We will conduct the extra session.
Please, sir, because I invested time in this, but I was not able to do it.
Yeah, this is a challenging problem actually. This maze problem is a challenging problem. Okay, now so check. Inside checks, there is no. Okay, now come to the week 10 contents. So this is the yeah. So week 10 is basically a string matching based week. So here we will learn the string matching, different type of string matching algorithms. So what is the meaning of string matching is basically when we match any patterns with in our text. So for example, if we have a document with a 1,000 words, and if we want to search or if we want to replace, so we generally use the replace or search or operation using the control F things. So how this matching will perform in the efficient way? Matching we can perform directly in the Python. So Python provide directly. You can use the strings in text, like so in one line you can find the strings. But how this matching actually is performed? So what algorithm is basically used to perform this task efficiently? So we will learn these different types of algorithms in this week. So we will start from the basic approach. So this is the brute force approach, nested scan from left to right. Okay, so here we are assuming that we have one text that is big, and we have one patterns that we want to match in our text. Okay, so both are the strings, and we want to match the pattern in our text, and we will return the starting index of each match. So you can see the concept of the. Okay, I'm explaining the concept how the naive approach we can perform. So for example, if we have a text, so I'm starting this A B C. Okay, and we have a patterns A B A. Okay, so this is a T and this is a P which we want to match. So in the naive approach, what we will do, we will just start from the first letters of the both. So P, we will just put this pattern here, A B A. Okay, we will start comparison each character one by one. So we will just put one variable here. So for example, I, and this is the variable J. And we will match the character of both the pattern and in the text. So we'll just compare that. If the value of I in our strings and value of at J are similar, we will increase the both pointer. Okay. So in this example, both are the similar. We will increase both the pointers. So J, like this, and we will check. Same things. We will this B is also matched. We will increase I and J, and then we will match this also. So this is also matched. So at that time, if we completed the pattern in our matching, so we will return the index of the I. Okay, first I. This. That means our pattern is matched at the 0 index. First, we will return value 0 here. After that, we will shift this pattern one position. So A, B, A. Okay, so we will shift only one position this pattern, and then we will check again. Because for example, if we have a pattern A, like this, so A, and our pattern is A. Okay, this is a text, this is a pattern. So if our this A, both A are matched, then we will shift this A one position, and definitely this pattern will match again. Because of that, we are shifting it one position after matching. So this is the one possibility of the pattern matching. So in the naive approach, we will shift the pattern on the one position, and then we will compare again. Okay, so B and A, that's a not match. We will shift one position again. A, B, A. Okay. Next time we will check A. So that means this A is matched with this A. We will check the second A, B. So that this is not match. Okay. We will shift one. Every time we will shift one position. When our pattern is not matching, or if our pattern is completed matched. So we will shift our pattern only one position. So this is a naive approach to finding a pattern. So at this time, this A will match, B will match, and A will match. Okay, so we will return 0, 1, 2, 3, 4, 5, 6, 7. So we will return this 3 index here. So that means our pattern is also matched from third index. Okay, so we will perform this operation sequentially one by one, and we will compare each character of the pattern with the text. So that operation takes maximum m into. So for example, n is the size of this text, m is the size of this pattern. So n into m time it will take. So this is a naive process to comparison. So this operation we are performing using this code. So you can see we are taking this POS list where we will store the matching index. After that, we are just using this one for loop I in range from len of t minus len of p plus 1. So this value we are taking because we need to shift only. So we will just reduce the index. So for example, the size of this p is 3. So we will shift this pattern till only this position. There is no need to shift this pattern after last position. Okay. So we will shift this pattern only this position. Okay, last pattern this will be matched from here A, B. This is the last position when we will match the pattern to our text. So there is no need to shift after that A, B, A. That means so there is no characters are available for this. So because of that, we are taking this I value len of t. That means the length of the text minus length of the pattern plus 1. Okay, and we are setting this matched equal to true. So we are initializing this matched equal to true, and we are just assigning this j equal to 0. So this j we are using for the pattern. This I we are taking for the text. Okay, and j we are using for the pattern traversing. And after that, in this process, we are performing this matching process. So while j is less than equal to len p and match equal to true, we will perform this operation. If ti plus j does not equal to pj, that means text character of the text not matched with the character of pattern. So at the time we will assign this matched value equal to false, and we will increase this j equal to j plus 1. So when the match value we are changing to false, at the time this while loop will break. And after that, we will check that if matched equal to true. So for example, all characters are matched of the pattern in the text. So definitely this matched value remain the true. At this time, we will check that if matched equal to true, we will append the index of the I here. So we will repeat this process. So this is the simple approach for matching the patterns in our text. So the complexity of this is n into n. So same things, we can perform this operation from the last position. So for example, in this case, if we are taking the text A, B, A, B, A, A, B, A. Okay, so for example, our pattern is A, B, A. So in the previous code, we have started the matching from the left to right every time. Okay, we can also perform this operation from the right to left. So at the time of the matching, we will start from the this position. If A match, that means this A character of this text is matched with the character of this pattern, we will shift here. Okay, so we will check the next character. So this is also matched, so we will move here. Now we will match this characters. Okay, so after all the matched completed, we will shift our pattern like this AB. Then we will repeat the process again from the last right to left. So both are the different way to match only, and the complexity will remain the same. Okay, nested scan from right to left. So after so here you can see that we have changed this condition. We have just initialized j equal to len of p minus 1. In the previous code, we have initialized with the 0. Okay, here we are performing matching from the last position. So this is the only change in the naive approach. Now, how we can
When matched equal to false, after that we are not breaking, but still we are going for j equal to j minus 1.
Yeah, so this match we are taking as a flag value. We have changed this match equal to false. This j equal to j minus 1 will perform. After that, we will check the condition. Here we will get this value as a false. So this value will break.
Okay.
Okay, so here we have taken two conditions: j is greater than equal to 0 and match equal to true.
No, but can we make use of break over here?
Break you can use here. Break you can use. So for while loop, break you can use. Yeah. So how we can speed up this brute force algorithms? Okay. So for speed up this brute force approach. So okay, I mean just explain an example: A, B, A, B, 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 B. Okay, and this is our text, and our pattern is, for example, A, B. Okay, this is our pattern. So for example, if we are matching this A, B, A. Okay, we will start from the matching from here. Okay, we will check that we will match the character one by one from the last position. This is matched. We will move here. Now this is not matched. Okay, this is not matched. So we will check that if A is not available before this unmatched character. Okay, so we will shift our pattern after completely after this index. But in this case, this is matched with so this A is also available in our pattern after this B before this B. So because of that, we will shift. So where is the position of this matching? So A is available here. So we will shift only one position for pattern. So A, B, A. Okay, at the time of mismatching, we will check that our mismatched character of the text is available before our mismatched character of our pattern. So if it is available, we will check the index. What are the index at which available, and we will shift the our pattern. So for example, there is only one difference between this B and A. One position is different, so we will shift one position of our pattern for that. Okay, so for the second time, for example, this B and this is matched. So I think we've taken one separate things. So for the clarity, Let's see. Okay. So at the same time, we will repeat this process. So B and A are not matched, but B is available before this A, and there is the difference of this A and B is the one position. So same things we will repeat. We will shift our pattern one time. So sorry, here A, B, A. Okay. Now when we are matching from the C to A, okay, so this is also not matched, then we will check C is available in our patterns, C is not available. So at this time we can directly skip completely, because if C is not available in our patterns after before this A, so we can directly skip 4 position. Okay, we will directly skip our pattern here in the next time. So A, B, A. So there is no need to match this C with every shifting. So every one shifting, because C is not available in our pattern. So we can directly skip 4 position for matching the next. So we will perform this matching from here. So B, A. So this B is not mesh. So we will shift 1 position here. So A, B. So this now the pattern is completed. So there is no need to match available. So this concept we will use in our first algorithms, Boyer-Murray algorithms. Here we will maintain a dictionary which contain the position of the last. So okay, I'll explain with the example these things. So actually we will maintain this information. If any character is not matched with our patterns, so we will check the position of the not matched character in our patterns, if it is available before that or not available. So on the basis of this, we will shift it our patterns for further matching. So the Boyer-Murray algorithm use this concept. So this is the code for Boyer-Murray. And what we will do in the Boyer-Murray first thing. So the first step is the pre-processing thing. So this is the pre-processing things here. Okay. This part is the pre-processing things. Before starting the matching, we will perform this operation last. We will create a last dictionary. And what the last dictionary will store actually for the patterns. So for example, if we want to match, taking the example from here. So for example, our pattern is A, B, C, A, B. Okay. And our pattern is, for example, P is A, B. Okay, so we will create a last dictionary. So last dictionary is representing basically this is a dictionary, and we will store this information last. So what character are using in our pattern? So A and B, 2 characters are using. Okay, so last A. So what is the index? So what is the index? Last index of this A is in our patterns. Okay, so this is 0, 1, 2, 3. So what is the last index of this A in our pattern? This is a 2. Okay, and same things, same information we will store for last B. What is the last index of B is 3. So this information we will calculate first in our Boyer-Murray algorithms. So if you can see that, so this information we are storing using this process. We are just traversing the patterns, and we are storing a last index of this of every character in our dictionary. So using this, we will perform our shift operations accordingly. So when we will get the mismatch, we will check that what is the last position of our mismatch value in this last dictionary directly. Okay, so I'm explaining this using a visual code. So I'll change the pattern. A B A B. Okay, so okay, so I'm starting this code. One sec. Sorry. Okay. So I have started the code, and now you can see the value at this time. So initially, last is empty, and you can see the value of each variable here. So p equal to ab, and our text equal to this. And after performing this pre-process, we will get this information. What is the last index of A and what is the last index of P in our pattern. Okay, now it is completed. So you can see the last index of A is 2 and last index of B is 3 in our pattern. So this information actually we are calculating in this pre-process phase. And we will use this information to shifting our pattern for matching. After that, we will start the process of matching. So basically here we will perform the same process which we are performing before. Match equal to 2, j equal to length p minus c. So same thing. So I'm just reading this value and explaining here. So what is the value? What is happening here? So A, B, C, A, B, A, B, A, B, C. This is our text, and our pattern is A, B, A, B. Okay, so we will start the matching from the first. So A, B, A, B. And our dictionary is A equal to, so what is the position of the index is 2. And so this is the last information you can see. And the last index of the B is 3. Okay. And we will okay, we will check that we will start the matching from here, A and B. So A, B. If A, this characters are not matched. Okay. If the characters are not matched, then we will check the position of what are the index of last index of A is. So this is 2. Okay. So that means this index is 2. And based on that, we will shift our pattern in that way. So if our pattern are not matched, so here matching is this. If matched equal to this, if matched, definitely we will increase the I by 1. If matched is so if elements are not matched, okay. So in that case, so here for example, so matched equal to while G is matched. Yeah. So at that time we will perform this shifting. J equal to j plus 1 we will increase, and we will read the value from our last list. So you can see this j minus last I plus j comma 1, which is the maximum. Okay, so actually this formula is used to shifting here. So what is the value of j? So okay, I have to check that what I is taking for the text, and j we are taking for the patterns. So one second. So I is here. And so okay, we are using this information basically. So I we are taking 0, and j we are taking 4 here. So j we are taking 3. Okay, so 0, 1, 2, 3. So j equal to 3, and I plus j we are matching actually. So I plus j 0 plus this 3 equal to this. So this pointer will come here. So when our mismatching is happening, so this mismatching is happening. So at that time, we will increase the j value. So you can see that if matched are not completed, is equal to false. So because we have already decreased j one time, so because of that here we are increasing it this once again. Okay. So after reducing j equal to 2, then we are increasing j equal to 3 once again, and then we will check that j equal to 3 minus what is the position, what is the index of last day. Okay, this is 2. So j equal to 3, 3 minus 2 equal to 1. That means we will shift our pattern only one position at this time, because this a is matched here. Okay, so for next matching we will shift our pattern here only one position. So a b a b. Okay, at the time once again we will check the pattern. So now this b is matched with this, a is also matched. Now c is not matched. Okay, c and b is not matched. So if then we will check c is available in our last list. So c is not available. If c is not available, then we will directly shift our pattern after that the c. Okay, so 2 position we will directly shift. So a b. Okay, now we will start from the matching. This is matched, this is matched, now this is also matched, this is also. When we get the matched completely, at that time we will shift our pattern only one. So a b. Okay, so same things here. Now this is not matched, we will check the last index from here. Okay, 2, and we will just calculate the shifting using the given formula in the code. So same things, we will get this one value once again, and we will shift this pattern a b. Now once again we have matched completely. Okay, so we will shift one position a b. And now the last thing, c is not matched with this b. Okay, so that c is not available in our last, so we can directly shift it completely, but there is no elements are available in this c, so that means we can stop this process. So we can save some comparison using these methods, the Boyer-Murray algorithms. So this is the code. You can see the patterns how we are going to in this code. So we are just matching the elements. So first elements are not matched, so we directly reach this position, and we calculated the last index. Okay, so what is the value of this max j minus last and this one? So at this time we will get this value. So we can directly write here. Do the console. This one value. Okay, so one value we are getting, we will shift the one position our patterns. So this type of shifting we are performing using the Boyer-Murray, using the last dictionary. So we will not match every time. We will not shift only one position. We will check the how many position we need to shift using this last dictionary. So using this method, we can save some comparison compared to the naive approach. So this is the concept of Boyer-Murray algorithms. So so you can, in some example, you can see the saving. So in this example, we did not see the complete thing. So for example, a b c. For example, this is our pattern a b c. Okay, and our so this is a text, and this is our patterns a b a. Okay, so we will start from this a b c. ABA, sorry, ABA. And whatever last dictionary is, so A is equal to 2 and B equal to 1. This is the last information. Now we will check the first character. So this C is not matched with the last character. Then we will check the index of the C in our last. It is not available. So we will shifted our pattern directly from here. So A, B, A. After that, same things. Here there is one mismatch. So at the same times, if C is not available in our pattern, we will directly shift our pattern completely. So A, B, C. Same things. Sorry, A. So this is also not match. So same things, we will shifted our pattern A, B, A. Now this is matched. Okay, so you can see the shifting. How many shifting we are performing here. So we shifted only one, 2, and in the so only 3 times we shifted our pattern, and last time we matched. So you can see the improvement of the Boyer-Murray algorithms. Otherwise, for the naive approach, every time we will shift only one position, so it will take the maximum comparison. Here we are just comparing the first character, and it is not matched. We are shifting the 3 position. Same things we are comparing. So how many comparison are happening only? So there is 1 comparison, 2 comparison, and 3 and 4, 5, 6. Only six comparison. We are just finding out that our pattern is available or not. So you can assume that how we can saving our comparison using this Boyer-Murray process. Okay, so this is the one algorithm for the pattern matching. So if any query in this, you can ask. Is there any query in this Boyer-Murray approach? Okay. So we'll move to the next.
Here we are matching from the right to left. That is why we are storing the last dictionary accordingly.
Yes, yes.
And we can also do from left to right.
Left, right. We can, yeah, we can also perform. Yeah, we can do. So at that time, we will store the first value, last value. So at that time, I think we have to store the first index, maybe. So if you will comparison the first value, then you will check that yes. At that time, you have to store the first index in the last dictionary for the shifting.
And that will be the only change. Rest everything will be same.
I think actually we have to check these things. Practically, it is working or not. Maybe I think it will work, but without implementation, I think we cannot say that exactly what change is required to do this.
Okay, sir.
So this is the Boyer-Murray approach, and we are improving our patterns, but still we will get the complexity is n into m. So for example, if our pattern is so here the example is also given. Our pattern is all a value. Okay, so for example, our pattern is all a. Okay, and our this is text. Actually, our pattern is b a a. Okay, so we will shift this b a a. So and in this case, we will just start from here. So this is matched. This is matched, and this last value is not matched. Okay, so at this time there is no element, so this is not so matched. This a is not matched with this b, so definitely a cannot become before, because this is the last element of the pattern. So at this time we will shift only one position. So BAA. Same things. We will compare first element from the last. Then we will compare this. Then at this time this is not matched. Okay, so last elements are not matched in every time. So in that case, we will perform M into N comparison in this situation. So worst case in this for the Boyer-Murray algorithm takes the N into M complexity. So in practically we can improve and improve our shiftings of matchings. We can improve our comparisons, but the worst case things is also N into M. So this is the one approach. After that, second algorithm is Rabin-Karp algorithm. Here we will actually perform the operation using a digit value. So for example, so for example, if we want to match the integer value in our string, so for example, we have a 1, 2, 4, 3, 5, 6, 2, 3, 7, 8. In our string, if we are containing this integer value, and our pattern is, for example, 2, 3. Okay, so pattern is 2, 3. So we will directly check that if so we will just read the value. So this is the length of the 2, and we will read the value 2 in our patterns, and we can directly compare this if 12 equal to 23. Okay, these things we can directly perform with the integer value. Okay, so this operation we can perform. So we will directly match this 12 value equal to matched with 23 or not. If it is not matched, we will shift our patterns one position. So 2 or 3. Now we will check 24 is matched with this 23. Here for matching, we will perform with the integer. Okay, so we can directly perform in this matching operation using it with the integer value. So 24 is not equal to 23. If it is not matched, we will shift our pattern here. So 23. This is also not matched. So same process at this time when we will move to this 23, this value is matched. Okay, so we can find out the index for the pattern match. So for string matching now, so this is the example for the integer value. So there is one code is given for these things. So we will read the integer value from the both. So this is a text and this is pattern. We will just read the value each time from the text and pattern of the pattern length and compare it. Here we are just comparing this numt equal to numt. If it is matched, we are just appending the index. Okay, so I think this 0 is not correct. Okay, so this numt equal to numt, if it is matched, we will add the index in our answer and we will repeat the process again. So same process we will repeat again and again, and we will match this thing. So this is the example with this integer value inside the strings. Okay, now how we can perform this Rabin-Karp algorithm on the strings? So we can just convert the string characters in the integer value. Okay, we can just make the mapping process. We can use any mapping process, and we can convert each character in any particular integer value. For example, if we are converting a into a 1, a equal to 1, b equal to 2, c equal to 3, so like this we can map every characters with an integer. So after that we can perform this task for the comparison, and we can find out the string matching. But still it will take more time, because here we are also performing the many computation things for the comparison. For example, this pattern is large, so in that case we have to match this large pattern with every value after shifting one position. So this large value comparison will take times. So there is another way is also to perform the 7 tasks. Rabin-Karp algorithm. So I'm just showing the slide. Boyer-Murray estimate Rabin-Karp. So this is the first approach. This example is given. And the second approach is that if we take in, for example, this our pattern is this. After mapping the characters into the integer value, so our pattern is this 3145. So you can see our pattern is p equal to this and t equal to this. Okay, so in that case we can take one q value and we will take this as a prime value. Yeah, so we will take one prime large value, and using this q value we will compute the mod value for pattern. Okay, so you can move to the here. We will compute the mod value for the pattern first, 31415. So we will just compute this 31415 mod 30. So we are getting 7. After that we will check this process in our text. So for text, so there are total 5 digits are available in our patterns. So we will take 5 digits every time in our text, and we will compute this mod value for each one. If we are getting the same value, then we will, after that we will compare the our integer value. So for example, 3, so in our text 23590, these are the first 5 digits. We will compute the mod value for this. So this 23590 divided by 30. So what is the remainder is this is a 8 value. So that means if the remainder value are not same, that means definitely the pattern is also not same. So but there is a chance two different value can generate the same remainder. So in that case we have to check.
Excuse me. What is
Yeah.
Q here? Q13, what is here?
This is a divisor value only.
From where it comes at?
We can take any prime number.
Oh, okay. Any prime number.
We can take any prime number. Okay. So or generally we take the large prime numbers to generate the unique mod remainder. Okay. So here this is one only example. So here we see that 23590 mod 13 is generating a 8 remainder. So this is not equal to our pattern remainder 7. So we will skip. We will not compare this all both value because the remainder value is different. Same for we will shift after mismatching. We will shift our matching pattern by 1 position. So next 5 value is 35902. Okay, so we will calculate the remainder for this is, so this is coming 9. So at the same time we will skip that. We will not compare this two, and same things we will repeat. But there is a chance we maybe we get two same remainder for two different values. So here you can see for 31415 mod 13 is returning a 7 value, and same for 67399 mod 13 is also returning a same remainder value. So 7 7. In that case, if we are getting a remainder value, same remainder value, then we will match our digit also with the pattern. Okay, so if we are getting the 7 value, after that we will match our digit value. So 31415 equal to this 31415 or not. So that will perform. So this is called the false positive actually. So if remainder is same but value is not same with the pattern, so that is called the false positives. Must scan and validate each block that appears to match. So because of that, so there are chance to get these false positives. So because of that we will validate these things. We will validate after getting the same remainder. We will validate the value is equal or not. We will compare the both value. Okay. So but where we are getting a different remainder, we will skip completely. So this is the Rabin-Karp algorithms. Okay, so this is actually a mathematical based calculation based using more things. We are comparing our pattern and text. So this is the only concept of the Rabin-Karp algorithms. Here the complexities also remain the same in the worst case. So for example, every time we are getting the same reminder. So in that case, we have to compare every digits. So we'll get the same m into n complexity. So this is the worst case for general alphabets is n into m. So this is the concept for the Rabin-Karp algorithm, where we convert the strings into a digits. After that, we takes one prime number to the as a divisor and compute the remainder for patterns, and then we match this remainder things for the text. If we are getting the same remainder inside the text, that means there is a chance for the matching. After that, we will validate after comparing the text and patterns. If we are getting a different reminder, then there's no requirement to the matching, so we can skip directly. So this is the concept of Rabin-Karp algorithm. And after that, string matching using automata. So automata, actually this is a very big area, but here we just use the diagram for it. I'll explain this. So what is the so for example, how we can use the partial matching information. So for example, if we have a pattern a b a b a b a, okay, like this, and this is our text, and our pattern is, for example, p equal to a b a b. Okay, this is our pattern. So, and if we are matching, okay. So we are putting here this a b a b. Okay, so if we will start from the comparison, so we will check that these things. So this AB is matched. Okay, so if you see that we will match this B and A, so this value is not matched. So I think in the automata process, okay. Okay. Here we will start from the left to right. If this value is matched, if this is also matched, this is also matched, this is also matched. Okay, and the last value is not matched. In that case, how much shifting is required? So for example, in this case, if our pattern is matched, so like this B, before that, so how much shifting is required? A, B, A, B. So our first value is matched, second value is matched, third is matched, fourth, and this is not matched. So in that case, so you can see that before mismatch, our this AB part, so this AB part is matched with our this AB part. Okay, this is completely matched, but this AB part is also a prefix of our pattern. Okay, so this, you can see this AB part is also a prefix of our patterns on this one. we have already matched this AB in our pattern, and this AB part is also a prefix of our pattern. That means if this AB is matched with this AB, and that means this is also should be matched with this prefix part, because this AB is a prefix of our pattern. So at the time of shifting, so we can use this information. If any part which have already matched in our patterns, and that is also a prefix in our pattern, so that means that the suffix part, so there is a part of in our text which matched with the suffix in our pattern, and so there is no need to compare again with this to a prefix. So for example, this AB, we have already matched with this AB, and this AB is also a prefix in our patterns. So that means after when our mismatching happen, so we will shift our pattern and we will not match with this pattern prefix part in our text part again, because we have already compared this part. Okay, so there is no requirement to match this AB to AB again. That is called the partial matching things. So we will shift our pattern from here. So we will shift our pattern AB, AB, A directly. That means, and we will start our matching from here. Okay. And that means this part is already matched. We have this information. This AB part is already matched before. So we will start matching from here. That means we will start comparison from this position. So this suffix and prefix information, if we can calculate, so we can also use this information for in our shifting process. So if any part of the text is matched with the suffix part of the pattern, and that suffix is also a prefix in our pattern, so we can skip this prefix matchings with the text. Okay, so how we can calculate this information? So what part of the pattern is a prefix? Okay, so this value we can calculate using a.
Sir, here AB, 4 characters were matched, and why didn't we shift 4 times?
No, 1 second. So here pattern is A, B, A, B, 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 A, and our this is a text. This is pattern A, B, A, B, A. Okay. So what you are saying?
First 4 characters of the patterns are matched in text. So, I mean, if these 4 are matched, then we need not match it again. Basis that principle, why are not we shifting 4 times, 4 positions?
But there is a chance to, so this AB we can put here, no? This position, this A and A matched, B and B matched. So for example, after shiftings, okay, I'm just changing the text here a little bit. Then you can see. So A, B, this. This. One second. B, this is. Okay, so accepting this. Okay, now you can see. So for example, this one. Okay, so you are saying that the 4 characters are matched. Okay, so these 4 characters are matched, and if last character are not matched, so why we are not shifting 4 position? So if you will shift the 4 position, that definitely your comparison will not match. So for example, I have also skipped this A things more. So if you are shifting 4 position, so A, B, and B. So that will also not match. So that means your pattern is not in the text. But if you see the text, pattern is available. Pattern is available from this to this one. Okay. So this situation we cannot avoid. Pattern is available in our text, but according to you, we will shift the 4th position. We will lose this pattern matching. Because
So
of that, we are.
basically, different characters which are repeating, then only taking a substring of the length in which there are different characters. Only that matching has to be shifted. Suppose it would have been A, B, C, A, B, C, A kind of thing, then we would have shifted 3 times.
A, B, C, A, B, C, this type. So for example, this A, B, A. So this is not matched, we will shift completely. This type of things you are saying?
Yes. No, I'm saying the pattern is ABC, ABC, a substring having 3 different characters. So we need
3.
to look for a substring which is having different characters and grouping them together. Like in ABAB, A and B are different characters and we are grouping them together. Correct?
Yeah, so this type of things, information actually we are talking about. If some partial part is repeating in our pattern, so there's no need to check again for the matchings. So because of that, we are this. I'm saying this information partial matching we can skip to match again. So in this pattern, A, B, A, B, A. So you can see that this A, B, A is a suffix also. This A, B, A is a prefix as well. So if this A, B, if we see these things, if we see this part, A, B, A, B. If this A, B is matched with this our text, so that means we have matched this AB. That will also match with this AB. If our half part which are
Yes.
repeating in our patterns, if it is already matched within the text, so that means this is also matched within of our suffix prefix part also. So this repeating matching we want to skip in this process.
Okay, sir.
Okay, so actually we want to find out that what is the suffix actually in our patterns that is also a prefix. So I'm generally okay. So there is one next algorithm, a KMP algorithm. So before that, there is one methods explaining in the lectures using the finite automata, but both are the same. Both are on the same concept. So I'm just explaining this using. So for example, if we have a pattern P equal to A, B, A, B, A. So we will check that for each for each substrings in our patterns, what are the suffix part is equivalent to our prefix. So for example, this A, if we just consider this A, so this is A, and this is the first character. That means this is also a suffix, and so for the same length, we will not check these things. So the value of the matched is 0. We can take if we will take the AB. Okay, so in this substring, you can check is there any part which is available as a suffix and also available as a prefix. There is no part. Okay, here the suffix is B and prefix is A. Both are the different. So same things we can contain this information here 0, and in the next substring A B A. Now you can see here there is a character A. This is a suffix in this string, and this is also a prefix in this string. So what are the length of the suffix that are matched with the prefix? So here 1. Okay. Now we increase the next substring part A B A B. So what are the maximum length of the suffix which are matched with the prefix here? Can you see? What are the maximum length of the suffix in this strings which are matched with the prefix also? So we can see that this AB, this is a suffix, and this is matched with this AB. This is a prefix of the system. So what is the length is 2. So we can write here this information 2. Okay. For the next A B A B A. So what are the maximum length of the suffix which matched with the prefix here? So we can see that this ABA is matched with the prefix. So this ABA is a suffix which matched with the prefix of the substring. So this AB. So what is the length of this is 3. So using this information which I have calculated here, we can skip some matchings. We can save some matching using this when we are shifting. Okay. So this information actually we want to compute in the next algorithms. So what are the portion in the patterns that is also a suffix and that is also a prefix? What is the length of that is? Because if we have matched the suffix part in our text, and that suffix is also a prefix in our pattern, so there is no need to match again this prefix to the text in the to the strings in the text which we have already matched with the suffix. Okay. So for example, ABA, ABA and BA. So if we have matched with this ABA in this text part, so for example T1, this is the part of the text. Okay, this is the 3-character text. We are just naming it as a T1. If we have matched this T1 with this ABA, so after that there is any text also available which are not matched. Okay, so we will not match this T1 in this ABA because we have already matched this part with this ABA, and this ABA is available also as suffix. So we will skip this matching again, and we will shift our pattern. So we will shift our pattern this ABA to this T1 position, and we will not matching all the characters of T1 and this ABA again, and we will start directly from the next character after the T1. So this information actually we want to calculate. So same things. So this prefix prefix suffix information we will use. We will calculate using the finite automata. After that, we can find out the pattern matching. So if you see these patterns, so yeah. So for patterns, so here one pattern is given. So there is one pattern ABA. Okay. So how we can calculate? How we can create a finite automata things, and what is the finite automata? So I'm taking this example, and how we can create a finite automata. So basically, finite automata we used for the string matching also regular in the regular expression for and the string matchings concept. We use the finite automata things. So we will create a finite automata for. So here this part is a text and this part is a pattern. Okay. So P equal to A B A B A C. So we will create a finite automata for this pattern, and for creating a finite automata we will take the states. Actually, finite automata contain the state and the transition. So that means, for example, if we have a 1 and 2 and 3 states, and this is a final state and this is the initial state, and every transaction we just contain any character. So for example, this P, and for A like this type of thing. So this type of the automation is called the finite automata. So we will always start from the initial state. So for example, this is a starting state. We will always start from the initial state, and we can check that our string pattern is matching or not. So we can, if we are moving, so for example, we have a string AB. Okay, so we can see that our AB is accepted or accepted this using this finite automata or not. So we will traverse the character and move to the next state accordingly, according our transaction or our edge. You can see here. So for example, first we will read the text A, and from the first state we will read the A character, and we can move to the second state. Okay, so we will move to the second state. After that we are reading the B, and we from the second state we can read the character B, and we can move to the third state. So at any time when we are completing this completing our strings and we are at the final state, so we can see that our string is accepted by this finite automata. Okay, so same for example, so A B A B, this string is accepted using this finite automata or not. So we will check again. So we can move from one state to 2 by A, then B we can move to the third state. After that we will read A. So by reading A we can move back to the second state. After that B again we can move to the third state. So after completing the strings, if we are at the final state, that we can see that this string is accepted by our finite automata. So using this approach, we can also use this approach in our string matching concept, pattern matching concept. So we will create a finite automata. So this is actually a automation diagram. So we have to create this automation to check our string is matched, accepted or not. So how we can create this finite automata for our patterns. So after creating this finite automata for pattern, we can check our text is containing this pattern or not. We can check. Okay, so for we have a B C, 3 type of character we are using. So that means our input is A, B, and C. Okay, and we have, so here A B is 6 characters we are taking continuously. So we can take the one more state. So we will start from the 0, 1, 2, 3, 4, 5, and 6. We will take the 6th state because we have a 6 character in the pattern. So we will take the 7 state from the 0. So these are the 7 states, and we can directly write these things using A, B, A, B. So this is actually initial state, and this is a final state. So this is a initial state, and this is a last state, is a final state. So A, B, A, B, A, C. Okay. So when we are at 0 state, we can read the A input and we can move to the one state. Okay, so this is the moving process. But what about if we are at the 0 state, and what if our input string is B? So we have to find out the other transaction. So this is the transaction according to our patterns, but we have to find out the other transaction also. So for other transaction, we will just create a table. So for example, so this is our pattern. A, B, A. Okay, so this is our state. So 0, 1, 2, 3, 4, 5, 6, and okay, 6 is last. And this is our pattern. So pattern. So what is our pattern is? So A, B, A, B, A, C. Okay. So we will fill all the information when we are at 0 state. If we are reading, so okay, this is C. Sorry. This is the third input, C. Okay. So when we are at the 0 state, we can move to the 1 state when we are reading A. So we can directly write the 1. Okay. So this state we can directly write in our tables. So from 1 to 2. So 1 to 2, when we are reading B, we can move to the second state. From 2 to 3, so 2 to 3 using the A. Okay, so we can write 3 here. So from 3 to 4, B. So this is 4. And 4 to 5 is A. 4 to 5 is A. And 5 to 6 is C. So 6 is here. These are the transition. And what are the other transitions? Now we will calculate that. So for example, we will check that. So here we will check this suffix and prefix things. Okay, so we are actually creating, we will use this suffix prefix things in this finite automata. So we will check these things. So at the initial state, when we are 0 state. So if any characters are coming, for example, if A is coming, then we will move to the 1 state. That means one character are matched with the text. But if B and C are coming, so that means we will check again from the 0. So that means if we are at the 0 state and the B character from the text is coming, so our text is for example, B. So that means this is not matched. First character is not matched. So same things, we will not move to the any states. We will stay on the same state. So for this is for the first. And for the next, for example, if we want to fill these things. So now our pattern is now A, B. Now we will calculate these things. What are the suffix length which are matched with the prefix length? What are the maximum suffix length which are matched with the prefix length? So there is no matched here. So we will put 0 in both places. Okay. No, sorry. I think this one part. So this is our pattern actually A before that, and we are filling this value. Okay, so after A, if we second A is coming, okay, after A is second A is coming. So actually we are just reading this value in our text. So we can say that what is the maximum length of our suffix which are matched with the prefix. So this is matched with, so the length is 1. So we can directly write 1 here. Okay. If after A, C is coming, A, C is coming. So that means there is no prefix match with the suffix. So we will put the 0 here. Same things for the next row, AB. Now before this third row, AB pattern have already come, AB. After that, if we are taking this B value, okay, B value. So you can see there is no suffix prefix match in this pattern. So we will directly put the 0. And if after that A, B, C is coming, okay, after A, B, if C is coming, so same things, there is no suffix prefix match in this part. So we will 0 put here. Okay. Now for the next, now A, B, A. A, B, A string have already come, and these are the two places empty. So A, this is for A. So if we are taking A, B, A, so is there any matching in the prefix and suffix? Yes. So this is matched with this. This is the maximum match with the suffix and prefix. Okay. So length is 1. So we put 1 here. For the next, if we are taking C, so A, B, A, then we are taking C. So that means there is no suffix matched with the prefix. We will put 0 here. For the next row, so A, B have already come. Now we are putting here. So for B, if we are taking B, okay. So you can see this 3 length is matched with this ABA. Okay, no, sorry. Yeah, so there is no matched with the suffix and prefix because this is ABB and this AB. So there is no match in the suffix and prefix. So we will put 0. And if you are taking ABA and then C, BAB then C, so that is also no match. Okay, so after that, so A, B, A. So in this place, if we are taking A, okay, so that means this is matched with this A. So that length is 1. If we are taking B, so A, B, A. If we are taking B, so that means AB. This part is matched with this AB part. Or there any length? No. Okay. Oh, okay. So AB, this is matched with this AB. Yeah, so the length is 4. So yeah, this is the final table. Now we can make the complete finite automata. So from state 0, if we are reading B and C, that means we will remain at the same state. So that means B and C. For state 1, if we are reading A, that we will move to the same state, A, and for the C, we are moving to the 0. C. Okay. And for the second state, if we are reading B, A, from the second state, if we are reading A, we are moving to the third state. And for the B, so okay, for B and C, so for the second 0, 0. Okay, so this is 0, 0. So from second state also B and C. And from the third state, so this is for the B, fourth state. For A, we will move to the first state, A, and for the C, we will move to the 0 state. Okay, and same for the fourth. So we will move to the 0 state for both B and C. Okay. And for fifth state, if we are getting C, we are moving here, and if we are getting B, so, okay, so B at this time we will shift here, B, and for A we will shift here, 1. So this is our finite automation for the pattern. So after that, if we are getting any, for example, if we are getting any text, so this is our text AB, AC. Okay, so we will check that if this string is accepted by our finite automata or not. So you can see that this is the first character A. Okay, so for the first character A, you can move to the one state. After that, B, you can move to the second state. Then A, you can move to the this 3 state, and then B, you can move to the 4th state, and then A. So yes, we can move to the 5th state, and then B. So at then B, we will move back to the 4th state. Okay, we will move to the back state, and then once again A, we will move back to the fifth state, and C, then we will move to the sixth state. So you can see now we after complete in our text, we are reaching at the final state. That means our pattern is available in our in the text. This information is returning these things about pattern. So this finite automation is so this text string is accepted by this finite automation. So we can see that our pattern is available in our text. So this transition actually is representing the suffix and prefix thing. So actually we have calculated this suffix and prefix part to fill this table and for the transition. So if any suffix are matching with the prefix, so there is no need to match again. So accordingly, we will move to the previous state. So this is the things using the finite automation, where we are using this partial matching information using the suffix and prefix matching. So same concept actually used in the next algorithm, KMP algorithms. So this KMP algorithms, this information, what are the suffix and prefix match, partial match information is calculated by this pre-process function, KMP fail function. Okay, so if you see that, if I run this code, yeah, so this is a KMP fail function. Actually, this is calculating the same information. What part of the suffix is matched with the prefix? So this is a pattern actually, and for this pattern we are calculating the this information. So I'm just running this code. You can see that what is the answer. So this list is calculated by this fail function, and we can see the things here. Okay, and so our pattern is this. Okay, so this is our pattern: A B C A, A B C A, A B C A. Okay, so we are calculating this information. I've already explained in the previous slide. So for A, so if we are taking this A part, so there is no prefix and suffix with the same length we will take. Same length we will not consider the suffix and prefix. So we will consider that this value as a 0. So actually we will start the calculation from the second character. This information, only one character cannot contain this information. So for AB part, if you see AB part, so in this substring we can see that there is a no suffix which match with the prefix. Okay, so we will contain this information 0. And next substring A B C, now you can see that there is no suffix available which match with the prefix in this. So same things, we will contain the 0 information. And now next parts A.
So can we look at it this way, like start of the pattern, if the beginning say 4 5 characters are all different, then all those 4 5 characters will be 0.
Yes,
In the
if
beginning.
initial A B C D E, these are the initial characters are coming in the initial part. So value for all these are will remain the 0.
Yes, why? Because nothing is repeating.
Yeah, nothing is repeating there. So because of that, we are checking this things, any suffix and prefix matching, and with the maximum length. So for if we are taking this A, B, C, A. So in this thing, you can see that there is a suffix available which are matched with the prefix. And what is the length is 1. We will take 1 here. Okay, so for the next A, B, C, A, A. So same things. The maximum length of the suffix which matched with the prefix is 1. Because I've taken this. So now next is B. So A, B, C, A, B. Now you can see this, the length of the suffix matched with the prefix is 2 maximum. We will put 2 here. And for the next, so A, B, C, A, B, C, A. Oh, sorry. So here you can see this ABC is matched with this ABC. Okay. So because of that, this 3. Okay. And last is A also. So this ABCA is matched. Because of that, I am taking this 2. So this information actually is returning by this KMP fail function. So this is the part of the KMP algorithm. So this is the pre-processing part of the KMP algorithm. We are calculating this information. What are the suffix and prefix matching in our pattern? So after calculating this, we are using this prefix information, fail function information in our KMP algorithms. And based on that, we are performing our shiftings. So in the previous diagram of the automation, so when we are reached at the first, so when at the time of A, B, A, B, A, B, and after that we are getting this C. Okay. No. So A, B, A, B. This part is matched. A, B, A, B, A. This part is matched, but the last character is not matched. Okay. With this, C is not matched. So in that case, the text character is B and our pattern character is C. So we are returning here at the last position. So here from we have reached at the 5th state, and when we are reading this B, we are moving to the only one position back. Okay, because before that 3, so AB, yeah. So this before this mismatch character, so these 3 characters are already as available as a suffix. Yeah, so prefix, this is a prefix and this is also a suffix. So on the basis of this information, we move only one position back, and we start the match. We start the shifting process again. So for the next character A, we move to the 5 and then move to the 6. So same things, same concept. Actually, we are using the KMP algorithms, but here we are performing using the codes. So using this fail function, when we will get the mismatch information. So we will read the value from the fail function, and we will shift according to that. So for example, I'm just running the complete mode. The complete now. The same. This is the pattern. Okay, so now you can see what is the returning why the function is. Actually, we call the find KMP algorithms, and so here you can see that we call the find KMP algorithm. This is a text and this is a pattern. And inside the find KMP algorithm, we just call this KMP fail function here with the pattern. So for pattern P, we are calculating this fail list using this KMP fail function. So this part is calling, and we will get this information here later. Okay, so after calling this, we are getting this list information, this fail function. You can see the value for the each index 0, 0, 0, 1, 1, 2, 3, 4, which we have calculated here. This is 0, 1, 2, 3, 4. And we will use this information in our pattern matching. After that, in the KMP algorithm, we will just start the process of our matchings at any time. So here we will start the matching from the left to right things. Okay, so left to right things, we are started from the 0 index in the both of the text and pattern. So this is for the text and this is for the pattern. If any time during the matching, if our k value is reached at the last value of with the so if k value is reached the with equal to the length of the patterns, so that means our pattern is completely matched. So at the time we will store this matching index in our match table. Otherwise, if our first character is, so for example, our characters are matched, so we will shifted our uh, I, j and k by 1 both. This is the, if the value are matched. Okay, if our value is matched, then this is the checking if our pattern is completed. So that means our complete pattern is matched. Otherwise, we will increase the j and k by 1 to check the next character. If our pattern is not matched, so if our text characters are not matched in the text and pk, so this is the part elif condition. If k is greater than 0, so for example, increasing at the third index or fourth index, our pattern characters are not matched. So we will read this fail list value. Here we will read this value. What should be the next position of the pattern to match in our text? So we will read this information from our field table. So this is written by our KMP fail function. So we will shift our pattern like this. So for, okay, I'm just starting from here. I'll take this diagram. Okay, this is. Okay. So for this A, B, A, B, A, B, B, A, B, A. This is our text, and we are starting process from here. So A, B, C, A, B, C, A. 2, 3, 4, 5, 6, 7, 8, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So we will start comparison from here. This is matched, this is matched, this is not matched. Okay, so this is for I. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the index of this is 0, 1, 2, 3, 4, 5, 6, 7. Okay, so we are taking this value is a k and this is a j. I think so. We are taking this. So j and k we are taking. Okay. So if our characters are matched, we will increase both by 1. So after when j is reached at the 2 and k is reached at the 2, there is one mismatch happen. Okay, so at this time we will check the what is the value of our fail function. So we will just reduce the k value by 1 and check that what is the fail function value is for the b is. Okay, and what the fail function value for this b is 0. Okay, this is representing a, b, c, a, this type of things. Okay, this is also clear here. So we will check this, what are the fail function value for b is 0. So that means we will shift our k at the 0 position. Yeah. Okay, and now our next matching will be start from here. So this part, this value is not matched, and we will compare our character matching from this this a and this first character in our patterns. from. That means this first A is matched with this A or not. Then this B is matched. Then now once again, this is not matched. So same things, we will repeat the process again. Now we will compare. That means we will shift our pattern here. So A, B, C, A, B, C, A. Okay. So now we will say comparison here. A is matched. So this is matched or not. This is not matched. So same things, same information we will read from the field function, and we will shift accordingly. So what should be the value of the k if any mismatch happen? So we will read the field function value from here if not mismatch. If this is happening when k is greater than equal to 0. If k is 0, so we directly increasing the j value. Okay. So for example, this last else condition is representing when the first character is not matched. So in that case, there is no need to increase the k value. We will just increase the j value here. So these are the three conditions in the KMP function. Here we are using this prefix and suffix matching things. So in this, actually, there is no pattern matching the list things, but for this example, we can see that. So this perfect example. Okay, so for example, this is text, and our pattern is example A, B, A, B. Okay, I'm taking 4. So what is the field function is? So field A function is, so this is 0, this is 0, and this is 1, and this AB, this is 2. Okay, so for this pattern, field function will be this, and after that we will perform the matching process. So A, B, A, B. Okay, so this is matched. So when we are getting the matching completely, we will shift the one only. So here, so once we will shift A, B here. Okay. Now we will check the first character are not matched. Okay. So in that case, we will shift only one position. So we will shift the one position of in the text. Okay. Now we will match. That means we will match from here. So A, B, A, B. So in that case, now this A is matched. Now this B is matched, A is matched, but this is not matched. Okay, so this is not matched. In that case, we will check the what is the fail value of this A, third position. Okay, this is a 1. So that means we will shift our k value at the 1 index. Okay, so our k will be start here, and our j will remain same. J will remain here. Okay, that means this A is matched already. This A is matched with this part. We will not match again, and then we will start the matching from here. This is not matched. Okay, so our shifting is here like this: A, B, A, B. So first character is matched. Second is not matched again. So the second fail function value for the not previous characters. So yeah, this is a 0. So that means we will shift our k at the 0 position. So this will shift like this: A, B, A, B. Now first is matched, second is matched, third is not matched. Okay, so we will check the fail function for this B. Here this is also 0. That means we will shift only one position. So A, B, A, B. Now first is not matched, shift only one position. So A, B, A, B, like this. So this type of shifting we will perform according to our fail index, fail information. So if any part is already matched with the suffix, so we will not compare the again with the suffix if both are equal. So this is the concept of KMP algorithms. So these are the main algorithms of this week. So Boyer-Murray algorithms, Rabin-Karp algorithms, and this KMP algorithms. And finite automata is only just to explain this KMP algorithms. How we are just checking with this. And after that, subtopics are also remaining. So tries and regular access. So 2 topics are remaining. So if any query, if you have in these topics, the remaining topic we will discuss in the next week after the quiz. We will conduct one extra session. So at that time, maybe you will also watch the video at that time. So at the time you can ask the more query. Yeah. Yes. Yeah. Goraja. Is there any query?
Nothing. Just
Oh.
So when will be the next session?
So for week 10 we will conduct in the after the quiz,
Okay.
if any day. So on Thursday or maybe on Tuesday, because Wednesday is already session for the week 11. So we will conduct in any day.
Before that, can we take extra session for week 4?
Only for week 4. Okay.
I mean those PPAs.
Okay. Yes, sure. We can conduct extra session for PPAs. So in next week we'll so there are one session on Wednesday. So there is one session is also on Friday, live coding for week 10, and one we will conduct for the week 10. So 3 and okay, we will try. If any slots are available, actually slots is actually the problem. If any slots are available, we will definitely schedule. So we will definitely discuss these 2 problems in any one of the sessions in the after the quiz.
Okay, sir. Thank you.
Okay. Okay. So tomorrow is the first revision session. If you have any query, you can ask in the tomorrow from week 5 and week 6. Our timing is 8 to 10.
Tomorrow it will be like a revision of concepts already covered, or it will be kind of query answer session.
I don't know. Bhaskar will take the session. How he will take? Maybe he will take some questions.
Okay, sir.
Otherwise, discuss every topic one by one will take lots of time. So
Yeah, we'll also collect our queries.
yeah. So maybe he discussed the concepts by taking some questions.
So the
Okay.
previous term questions will be discussed tomorrow.
So if you have any query from the previous term questions, you can ask. Okay, just collect the questions which you are not getting the concepts for the questions. You can ask in that session. So questions are actually lots of questions are available. So if you will consider all the questions, so it will take also lots of time. So just collect the question which you are facing the difficulty, and you can ask in this revision session. Okay, any other query or shall we close? Okay. Okay, thank you all.
Thank you.
Thank you,
Thank you,
Jaggu.
sir. Thank you.
Good night.
Good night.